guys, today we are working on solving nonlinear inequalities. I'm going to refer back a few times to the sections, where we dealt with these kind of equations because you're going to want to refer to those. And I think that's all I have for you. Have a lovely evening. So there are some basic steps involved in these. First, you're going to solve the problem as though it were an equation to find the boundary, or in some cases, boundaries. Place those boundaries on a number line to determine the possible solution regions. Then from those solution regions, pick a couple of various numbers. Definitely don't pick the boundaries. And then evaluate those values in the inequality to determine if they're true or false. Once you have figured out your solutions in the once you've figured out which regions work and don't work, you're going to write your inequality as well as interval notation based on which ones were true and which ones have the or equal to or not. So the examples help with those steps, but those are the steps you definitely want to have down. And there's some variations depending on the type of nonlinear. We're going to be dealing with solve the problem as though it were an equation. Quadratics, that was from section 1.5. Quadratics. So for the proficiency level problem, I am going to be giving you the boundaries. What I mean by that, step one was to, so what I'm going to do is treat it as though that equation has already been solved. This gives you the boundaries of -1 and 2. So what I mean by that is if I were to have solved x plus 6 equals x squared plus 4, got everything to one side, and solved that using quadratic formula or factoring, I would have ended up with x equals -1 and x equals 2. So we know we have those boundaries, so what we're going to do is place those on our number line. So we got -1, pardon me, and we have 2. So now we have a couple of solution regions we want to look at. Over here, we have any number of things that could work. I could try x equals -4. I could try x equals -8. I could try x equals -2. Anything over here I'm going to want to test. So I'm going to write x equals -5. We'll try that. From this middle region, my whole numbers are pretty limited. It's just 1, 0, and 1. 0 is one of the most easy ones most of the time, if you can use it, if it's not one of your boundaries. And then over on the other side, can pick anything over here. I'll go ahead and pick x equals 5. So then I'm going to take my original inequality and I'm going to test. So first off, I'm going to test over here. So I'm going to test x equals -5. Not really sure about my color choice there, but so my original inequality is x plus 6 is less than x squared plus 4. So I'm going to take out my x's and I'm going to plug in -5. Here I'm going to put it in parentheses. Then I'm simply going to simplify. And one of the things you want to remember is that when you're simplifying, you're taking care of everything on the left and everything on the right. You're not using any of those solving steps like subtracting 4 from both sides or anything like that. You're just evaluating both sides. So as I go down, -5 plus 6 is 1. I'm going to drop down less than, and then -5 squared is 25 plus 4. So I have 1 is less than 29. And that is a true statement. 1 is certainly less than 29. So this section, that works just fine. Next up, I'm going to test x equals 0 back into the original inequality. So x plus 6 is less than x squared plus 4. Once again, I'm going to take out my x's. This time I'm going to put in 0. This is why 0 was such an easy one to use, because it just kind of takes out a lot of stuff. 0 plus 6 just gives me 6. Drop down the less than. 0 squared is 0. And I'm left with 4. So 6 is less than 4. That is not a true statement. So I am going to X out that middle part. That's not part of my solution. Finally, I'm going to test x equals 5. So, got... And this can be kind of a long process sometimes. But once you get used to it, it goes fairly quickly. It's just at first when it's a little clunky. All right, so I get my 5 in there, positive 5 this time. I have 11 is less than 25 plus 4, which is 29. That is also true. So I have this part over here that works. So what I found is that my solution region is anything over here as well as anything over here. So the main reason here that I put 2 number lines is because the first one, obviously, I got a little junked up. So what I'm going to do is take my boundaries, -1 and 2, and I'm going to put them down here. This time I'm going to put them as open circles. The only thing that we really use from the beginning symbol here is knowing whether this is going to be included or excluded. In this case, it's less than rather than less than or equal to. So I'm going to put open circles at -1 and at 2. And then I know, based on what I did up here, that this region over here worked, as did this one, but the one in the middle did not. So those are going out to the right and out to the left. So what that tells me is in my final answer, I have to figure out what my inequality notation and my interval notation are. For this region down here, this is telling me that x is less than -1. So that's part of, sorry. And then I'm going to write or, because the other part of this, where x is greater than 2, it can't be both up here and down here. I'm not going to have a single value that will be less than -1 and also greater than 2. So I have to write this as 2 separate inequalities. So x is greater than 2. That's my inequality notation. My interval notation, smallest to largest, always go smallest to largest. I have -infinity up to -1 with a parentheses, not a bracket, because it's not included. The union symbol, and 2 out to infinity. So you always want to go in your interval notation, lowest boundary up to your highest boundary. So -infinity to -1 or 2 to infinity. So that is my overall answer. Now I'm also going to show you something that is usually true. Let's set the, whoops. Let's see what I can figure out here. No, not letting me do that either. All right. Nope, now I can't grab it. There it is. Okay. What I have here is I've graphed the line x plus 6. So I've graphed this side of the equation as though it was its own thing. And then I've graphed the parabola, x squared plus 4. And what I find is they cross where x is -1 and x is 2. Those were my boundaries that I originally started working with. So if I want to know where the line is less than the parabola, then I'm going to figure out where the line is physically below the parabola. So if I trace the parabola, the line is below it, until we cross at -1. And then the parabola dips below the line. And then the parabola again is above the line, so the line's below it. So that's how we end up with our areas over here working and over here, but not the middle part. So, sorry. Yeah, it's still not working the way I want it to, sorry. So, the only reason I wanted to show you that is to tell you that most of the time with quadratics, you can avoid testing 3 different parts. Now, if you test all 3 parts, that's fine. It's not a big deal. But you can also just test one point in the middle section. If it works, then that area in the middle is your solution. If it doesn't work, then it's the area to the outside. So parabolas are either going to be, quadratics, those inequalities are either going to be between 2 points, or they're going to be going away from 2 points. So it's either or. So if it doesn't work, if your point in the middle doesn't work, then you know it's going outside. But if you check all 3 parts, it's certainly not going to hurt. Absolute value inequalities from section, oops, I didn't write that on there. That was 1.6. My inequality. All right, next up, absolute value inequalities. All right, so we now have boundaries at -2 and 4. So just like we did before, we're going to put those on the number line. So -2 and 4. With absolute value, there's a couple ways to go about it. One of those ways is to solve it, get your boundaries, and then check for extraneous solutions. Whether you do that or you test each region like we did with the quadratics, you're going to end up probably testing three equations. So I'm going to go ahead and just test all 3 sections. I'm going to test a value down here. So I'm going to go ahead and test x equals -4. Middle, I'm going to test x equals 0. And up here, I'll go ahead and test x equals 7. Those are pretty arbitrarily picked except for 0. 0 is pretty specific. And then I'm going to put those into my absolute value equation. So first I'll test x equals -4. So absolute value of 2 times -4 plus 1, close my absolute value, is less than or equal to -4 plus 5. And then just evaluate. Inside here we've got -8 plus 1. Make sure it stays in those absolute value lines until you get totally done simplifying within them. -4 plus 5 gave us 1. -8 plus 1 gives us -7. Absolute value. So I've got the absolute value of -7, which is 7. And that's where I can drop the lines. And it is not true that 7 is less than or equal to 1. So I know that over here, where x equals -4, that region doesn't work. Next up, I'm going to test x equals 0. So I've got absolute value of 2 times 0, whoops, plus 1 is less than or equal to 0 plus 5. This one's quite a bit less work because of those zeros. The 2 times 0 gives me nothing, so I've got plus 1 left. So absolute value of 1 is less than 5. Absolute value of 1 is just 1. 1 is less than 5. That is true. So my middle section is good. So the last thing I'm going to check is x equals 7. The reason we check all 3 is because those extraneous solutions can have an impact. So test x equals 7. So I've got 2 times 7 plus 1 absolute value is less than or equal to 7 plus 5. So we've got, keep forgetting my colors, 14 plus 1, that's still an absolute value, is less than or equal to 12. So I have the absolute value of 15 is less than or equal to 12, which is just 15 is less than or equal to 12. That is definitely not true. So again, this part over here does not work. So what we know then is that our boundaries at -2 and 4, because of this or equal to line here, those are going to be filled in circles at -2 and at 4. And because of what we know up here, that this part worked and these parts did not, that it's the space between them. So this can be written as a single inequality, a compound inequality, and as a single interval. In the compound inequality form, we've got -2 is less than or equal to x, which is less than or equal to 4. In interval form, we have a bracket. -2 is our lower boundary, 4 is our upper boundary, and we close that bracket. So those are our answers to the absolute value. Finally, we've got radicals. And then radicals, no. Quadratics was 1.5. Yeah, that's right. Sorry. Radicals 1.7. Okay, so we'll go back. And this gets a little bit tricky. When we do this one, something that we have to watch out for. You cannot take the square root of a negative number. So anything from here down, you can't take the square root of. Square root of -4 is going to give you an error because anything times itself is going to give you a positive. So what we have to do is we have to create a wall and make sure we know what x can't be. So we take what's under the square root sign, in this case x plus 3, and we need to make sure that x plus 3, so I'm going to put this over here, this is why I have this space right here. We need to make sure that x plus 3 stays positive, which means it's going to be greater than or equal to 0. It's okay for it to be 0 because you can take the square root of 0, you just can't take the square root of a negative number. So this is this extra step. And apparently I can't write. Let's try that again. There we go. Extra step. This is only for any radical inequalities, but you have to do it. So I'm going to solve that inequality, -3, -3. So we know that x has to be greater than or equal to -3. And that's just to make sure, it's called a domain restriction. That is just to make sure that everything under the square root sign stays positive. So that's a wall. No matter what comes up in the rest of what happens on here, none of our x's can be down here. So what I'm going to do, so I'm going to take that, add that extra boundary of -3. So next thing I'm going to do is I'm going to add my boundary of 1 to my number line. And this time I'm only going to test one of my regions. Now, if we had x's on both sides, we would have to check more than 2 regions because you'd have more than 2 answers. But for this one, we only need to check over here and over here. I'm going to go ahead and, actually I'm going to use a number over here. I'm going to use x equals 6 to test. The reason I'm going to do that is because when I plug in 6 for x, I'm going to end up with 9 under the square root sign, which has a perfect square root. 9 is a perfect square. You can use anything and just put it in your calculator, but for the purposes of simplicity, I'm going to use 6. So I've got the square root My pen is not working well. Square root of 9 is greater than 2. So I have 3 is greater than 2. That is true. And if I want to double check and see if this part down here does not work, I can check with 0. So square root of 0 plus 3 is greater than 2. If I take the square root of 3, I get 1.7-ish. So 1.7 is greater than 2. That's definitely not true. So what I'm going to do is take my boundary of 1. I'm going to make it an open circle because of that sign up here. And I know that x equals 6 worked, so all my solutions are out to the right. In this particular case, my wall didn't end up mattering. So what I want to do is show you what that would look like if we switched the sign around just real briefly. Okay, just trying to figure out how I was going to do that. I'm just going to erase all this. Well, most of it, not all of it. Okay, so let's say instead, nope, not going to let me do that. Instead of greater than, radical x plus 3 is greater than 2, let's say I have, oh, here's what I can do. Oh, there we go. Let's say I have less than 2. So when I do that, I still have my wall at -3. -3, nothing past it, and I think I might have put the wall at -5 on the previous one. I hope I did not, but if I did, I apologize. And then we had our boundary at 1, and we had an open circle at 1. Now, if I test 0, in the new inequality, I've got the square root of 0 plus 3 is less than 2. So that's the square root of 3, which is approximately 1.7. And that's true, that is less than 2. Without our wall that we had created, we would think that any number less than 1 would work. So if we pick -8, what we would find is that we would get -8 plus 3 is less than 2, and we'd end up with -5. Square root of -5 is less than 2. But you can't take the square root of this. So the only x values that will work in this inequality are going to be the ones between 1 and -3, and they have to stop at -3. So instead of having that arrow, I can only go from -3, which is included in our solution, and 1, which is not because of our original sign. They're not totally original, but you get the point, hopefully. So then we would write it as a compound inequality. In interval notation, we'd have -3 up to 1 with parentheses and brackets. Whenever we're finding that wall, it's always going to be less than or equal to, because you can have the square root of 0. So hopefully that helps, and hopefully it's not all over the place.